this is the approach which I'm taking now since already 10 years, where I'm collaborating closely together with simulation folks. But I've never done a numerical simulation, so please don't blame me for having something stupid in the sense. The Darmstadt Engine Workshop is also a workshop like this, but it's meant to be a little bit more in the sense of a collaboration between experiment and numerical approaches. And my vision, and this was when I founded this together with Brian Peterson years back, that we use both approaches to learn more about the processes in the cylinder. And that's actually the final aim, goal of this effort. And the engine workshop takes place once a year, so you can, if you're interested in, just let me know. But we are collaborating also in the rest of the year together with all these groups and discussing results, and this makes it very interesting for me. So what we have learned yesterday already is that you need validation, and it is not sufficient just to do a validation on one. Let's say, if you look at this image here, on one snapshot at a certain Klein-Gangler degree. So you might match it perfect. But as I heard, like numerical dissipation or other stuff, when you match this, maybe at the end of the cycle, the flow fields may be completely different from your simulation. So what I learned is that it is important to validate the simulations along the entire engine cycle. This is one part. But the other part is you need to validate all the different processes, ideally many different quantities, to really make sure that what you're doing is correct, and that you also understand the sensitivities of the different models. And I think that's the crucial part of this exercise. Not about telling you about experiments, but I think understanding in which corridor my simulation is trustworthy. And that's the first step which we're doing in this approach, which is providing comprehensive validation data. But on the other side, we also have drawbacks in the experiments, and so I don't know how much you know about this. We can provide you nice, also colorful pictures, but maybe from a plane, or maybe from a thick plane if you use tomographic particle image velocimetry, but that's it. And so if you want to understand the flow in the cylinder, it's good to have information from the simulations. This is an open foam simulation, that's why I chosen this, from Andreas Kempf group in Duisburg. And you see nicely the tumble flow, which forms the nice component of the engine. And you see how the flows interact with each other, and you can learn much more about the causes of cycle fluctuations. And this is not possible if you only focus on experiments. And that's actually the fun part of this. And so I'm happy if anyone wants to collaborate within this context, please let me know. So the engine which I'm looking into is a single cylinder optical engine. And this is specifically meant for model validation. It's designed also for model validation. So you immediately see that the infrastructure looks a little bit strange. You have planums, you have straight tubes. And this is meant to have really well-characterized geometry, which is not easy if you have a casted engine with all the different parts, and also to provide you all kind of like pressures, temperatures, mass flows, lambda, etc., all over the line, which is monitored continuously to make sure that the engine operates reliable, repeatable, and that you have this information as boundary conditions. So this is the engine itself. Let's have a look into the cylinder. Okay. So it provides us the best possible optical access. We have a really large glass liner which goes all the way up into the pentile. We have a large flat glass piston. So this gives me the opportunity to measure as like anything which is possible with optical diagnostics. Of course, I need to have the diagnostic. It is a standard gasoline and spark ignition engine design with a pent roof with 2 intake valves, 2 exhaust valves, and a centrally mounted injector so that we can look into the different processes which are nowadays relevant. I want to keep it with there and not provide more details on this engine, but continue now on what kind of data we're taking. So I mentioned a comprehensive data set. This requires a lot of different properties. And we build up a sequence for validation starting from the, let's say, the most simplest case, which is a motor engine, it's no other processes, it's just intake air compression and just expand it again, that's it. But from there, because the turbulent flow dictates all the other processes, we really took care to get all kind of quantities which we were able to do, like the temporal evolution of the flow with high-speed PIV, where you have the flow field crank angle resolved. We provide information on gradients. We also resolve the boundary layer flow, where you saw yesterday the presentation from Max Asenzahl. He presented some of these data. But beyond this, you also need to have the boundary conditions. And this is a pain for engines because everything's continuously changing. And therefore, we took like wall temperatures over the cycle in different locations using thermographic phosphors, for example, to just provide you information on how the temperatures change. Also, another exercise was to measure gas phase temperatures, because if you have different intake temperatures, cylinder head temperatures, you don't know what the trapped mass is. And we figured out that the pressure trace, to capture it correctly from a simulation, it's not a trivial task, because you have so many knobs you can play with, you don't know the boundary conditions, and therefore iteratively provided more and more data, also measured blow by, etc., just to make sure to rule out all these issues. Then, once this exercise was done, we provided flame measurements in perfectly premixed air-fuel mixtures. Everything's homogeneous. Then we looked in flame propagation, looked how the flame modifies the flow field. But then at some point, the flame interacts with the wall. And that's also a very interesting part of the story, that we resolved the boundary layer flow and looked how does the flame modify the boundary layer flow. That's also a very interesting part of the story. Of course, wall temperatures is then another issue which we tackled. And the final step, we looked at direct injection. I've done this so far for liquid fuels, and where we looked at the spray penetration depth, mixing field, wall wetting. And therefore, I had this morning also the question, what is the influence of the turbulent flow? This makes completely different to all the data which is available on this CBC, this combustion vessel, these pressure vessels, I mean. So that's something which I'm still happy if someone has ideas how to continue, please let me know. I'm happy to provide more data if possible. So, but now this was the past with hydrocarbons. Now we're moving on to hydrogen. And since Tommaso asked me to talk about a topic which is relevant for you, I think that's good. And we just received first results in the last year, so I'm able to. So, just a short summary on the specific hydrogen characteristics, which are different. And I think you know all this. You have high flame temperatures, and so to reduce NOx formation, we diluted. So we did a dilution all the way to 60% of EGR, for example, and hydrogen burns. I don't know if it's how much unburnt hydrogen is in the exhaust. I haven't measured it yet, but you can achieve a stable combustion. Also for lean condition, it goes all the way up to maybe lambda 5. That's no problem for such kind of engine. But then you have the high diffusivity of hydrogen, forming the thermodiffusive instabilities of the flame. And I selected this figure from Heinz Pitsch group from a DNS where they can just switch on and off, like Lewis number effects, Lewis number 1 and a lean and a small Lewis number. And what you see here is just the heat release rate. This is 2.5 kilowatts per cubic centimeters, and looks quite uniform for Lewis number 1. But if you go to these lean or small Lewis numbers, you see that there's very strong variations across the flame. So you have regions where the heat release might double, and other regions where it's close to 0. So it has local effects. The question for me was: how much does this affect engine combustion? If we are interested in engine development, do we need to capture this? Do we need to address this? And this is, to me, an open question. And therefore, of course, the final step is low density, where you have all the under-expanded jets, and this was shown just, I think, in these days already. So, to tackle this, my plan is to following validation sequence for hydrogen. It's the same as I mentioned for the hydrocarbons before. we have already the motor data, so everyone who is familiar with this engine, he can stay with this. And from those known operational conditions, I will now add operational conditions using hydrogen. And starting with homogeneous mixtures, where mixing takes place in the port fuel port already, in the intake port, so that we have, again, premixed mixtures, want to investigate the flame dynamics, flame wall interactions, and then in the final step, add direct injection. And since direct injection has so many, well, it's quite different to all what we know, we added an intermediate step, like an injector in a co-flow. It's an atmospheric device, and this allows us to look at individual injections and to provide a mixture fraction field quantitatively using Raman-Rayleigh spectroscopy. In closed vessels, this is quite difficult. So this opens up this, and then we want to apply it into the engine, looking at mixture formation with no combustion and finally with combustion. And if possible, of course, I would also like to move to emissions and here NOxes. I think the topic for hydrogen. So now let's move on to some first results which we achieved here. So we started to look into flame visualizations, and hydrogen flames, they're barely visible. If they're lean and you have a burner in front of you, you won't see it and you won't feel it unless you really get in touch with the flame. And that's what we also observe in the engine. You cannot just use a high-speed camera. So what we use here is we add a small amount of sulfur dioxide as a tracer to the flow, and you can excite it with a laser, with UV light, and then it fluoresces. And the fluorescence is a function of temperature. The fluorescence increases with temperature, and so you can use it to differentiate between the burnt and unburnt region. I think, yeah, you see here on this figure, the blue region is like a high intensity region. This characterizes the burnt gas region. And so we can use this to detect the flame front. And here the setup is shown. I guess I don't need to give you more details. We just, maybe one short note, the laser is brought in from the bottom to the glass piston, which is somewhere here. And then we have a small laser sheet, which is to the right of the spark plug. Here you see the enlarged image. And in this region, I will show you now some first results of the hydrogen flame. So what we did was now, as a first try, to do a lambda sweep. This was done for our basic operational conditions at 800 RPM and 0.4 bar intake pressure. And we varied the lambda from 1.6 all the way to 3.3. And you see that the pressure traces are, the blue line is the richest case. This was an optimized combustion. And then we kept the ignition timing the same. I know that for engine people who are developing engine, that's not a realistic scenario, but it allows us to have the same thermodynamic conditions and the same flow field at ignition, because we are interested in the early flame. That's the reason for it. So we have these variations, and then you can look at do a statistics, a flame PDF, to see the probability where to find burnt gas region. If it's 1, that's the red color, you will always find burnt gas there. And so this gives you an idea of the flame, how it propagates. And from top to bottom, you see the richest case and the leanest case at the bottom. It burns slower. That's what we expected. So in the row, you see a crank angle after ignition. And this is 4 crank angle degree up to 7.6 crank angle degree after ignition. That's the first impression we had from the flame. If we look now into individual images, which is the right column, you see from the top for the rich case, the flame wrinkling looks more like we are familiar with from hydrocarbons, but the leaner it gets, the more structures appear. However, you can say, well, this is a selected image, and you always select nice images if you want to present something. So therefore, we did a statistical analysis of this and calculated flame surface densities. And since we only measure it within the plane, it's like the length of the flame contour divided by the area of the burnt gas. That's how we did this approach. And did this for this first quick analysis. We just draw a diagonal from the spark plug, fixed a region of interest, and moved it as long until half of this region of interest was filled with burnt gas. And then we determined the flame length for the phase. So with this, we can get like statistics of the flame surface density. And these violin plots, they show from left to right increasing lambda from 1.6 to 3.3. And at the top, we have 4 crank angle after ignition. Here's 7.6 at the bottom row. And what you see is the difference was not so much. We were a little bit disappointed, I need to admit. But you see some trend that for the very lean mixtures, especially if you wait a little bit longer, that maybe the instabilities have more time to evolve, I guess, that there is a trend that the flame surface density increases for the lean mixtures. This is what we expect and we hope to identify. However, we thought, well, maybe we should work on our experiments and to improve our hardware. For this, I just remember I want to show you a comparison with CH4, with methane, because that was something we thought, well, it would be good to understand what the difference is to our well-known methane database which we have. So we did, for this case, again, well, there are different options to adjust your engine. And we did now here an optimization where we said, well, it's optimized for methane, for lambda 1. And then we kept the ignition timing again the same, due to the same reason, to have the same thermodynamic conditions and flow field. And then just decreased or increased lambda of hydrogen until the pressure trace of the early flame lies, let's say, on top of each other. Of course, for later timings, they go apart, but that's not feasible to get them on top of each other because these are different fuels. There's no chance for that. However, we did this exercise, and then if we look at the surface density, flame surface density, we didn't see any difference. Unfortunately, we did not take the leanest case. So maybe for a much leaner case, we might have seen some difference. But it brought us to the idea, well, we should look further and try to improve our experiments. So, because so far, our spatial resolution was 200 microns for flame visualizations. So you see, it's hard to barely see, so I try to highlight, you see these small rings, there are some dark stripes in there, and they only appear for the hydrogen cases. For the methane cases, burnt gas region looks very homogeneous. So this brought us up to the idea, well, the DNS people, they see these nice finger-like structures, we also want to see them. What do we need to do for this? And I have some really smart postdocs and PhDs in my group who went back to the labs and tried to improve our hardware and our experiment. And where we started out with the experiment, which I just showed you, is the left upper corner, where you see from a Siemens star the spatial resolution. This is how we characterize the spatial resolution. So you take like the diameter of this structure, where you start to differentiate the different stripe structures. And spatial resolution for the high-speed camera was, with intensifier in front of it, was just 215 micrometers. And therefore, we were lucky to run into someone asked us if we want to test a new camera. And this is a UV-sensitive high-speed camera. And the only thing they did is just to replace the glass in front of the chip from a normal glass to a quartz glass. But I guess I have not seen the price yet because it's not yet on the market. I guess it will cost a little bit more. That's what my impression. But the good thing about this, because our SO2 signal is somewhere in the UV, we can now get rid of the intensifier. And with this, you see the structures are much clearer, and we were able to achieve spatial resolution of 33 micrometers with in-plane resolution. So therefore, we took now the next step and to also decrease our laser sheet thickness, which is now in the order of, let's say, 50 microns. Now, let's compare the different results which we have. The top picture is from our high-speed IRO, which I just discussed the results. You see a very stripy pattern, which is the high-speed lasers have a really bad laser profile, and it's quite noisy. Now, let's go look at the second row. It's the high-speed UV camera, but still using the high-speed laser. The image is quite dark. But if you go to a powerful laser, which are the classical 10 Hertz lasers, providing you just one one snapshot per cycle, not more, but you have much more power. And this is the lowest row. There you see nicely how we can resolve the structures much better than before. And now, if you zoom in this red rectangle, you see we optimize the experiment also in terms of the color bar. And then we really matched nicely from Pitch's group these DNS simulations, which are meant for similar, let's say, pressure and temperature conditions. They did a sweep of different conditions. And we were happy to see also these kind of structures. So you see all these diffuse structures, and these do not appear for methane. You can imagine for the 3D flame, also for methane, if you have two flames which are wrinkled moving towards each other, you also might have a gap like this. But the gap has a much higher contrast because there's unburned gas in between. As soon as they collapse, it's uniform. Here you have sort of differential diffusion or other effects. I need to learn more from you guys. We see that the result that the signal is lower is because the temperature is lower there. Because our LIF signal is a function of temperature. Unfortunately, we cannot say what the real temperature is, but that's the fact why you see these dark stripes coming in. And that, I think that's now a good situation where we can say, well, we see these finger-like structures even in such a turbulent scenario, which we were not sure if they show up because turbulence typically dominates many processes. So that's something which is now this is just work in progress. I have not more to show on hydrogen so far, but we are continuing to work on this, on the sequence. And if you're interested in this, please let me know. Brings me up to the summary. Strangely animated. So I just want to give you two key messages for today. I believe that a comprehensive data set is really essential for validation. And I think that's something we always should consider. And because we need to understand the sensitivities of the models and the simulation framework, there's no chance to avoid this. The second is that we were now able to also observe the thermodiffusive instabilities in an engine under these very lean conditions. And now the question is, what are the effects from turbulence? Maybe the wall might affect them later on if they impinge onto the wall. And I guess for the engine developers, the question is, how important are they? Do we need to capture? How much effort do we need to put into it? That's something I want to give you guys as a homework and want to learn more in 2 years when we have the next workshop. Thank you very much.
Thank you, Benjamin. I think you have a very interesting period ahead of you. A lot of things to do. Yeah, the floor is open for questions, so if you have, please let them know.
I have a quick comments. Very interesting and excited about this new data coming out. And for engine context, the most important quantity is after all these wrinkles and structure, we're not going to be able to resolve it in the simulation. What is its impact on the overall burning rate? So is there any reliable way to measure accurately your overall propagation speed of that setting?
In which sense do you think? I showed you like these flame PDFs where you see like on average of how it burns. That's how many people characterize it. You have the pressure trace where you can calculate heat release if you want. And so these measures are always available.
So is it really reliable? That's important, right? So what Heinz Pitch's group has been arguing is that that's the very lean condition. So the flame brush, which is all we can do in the engine type of simulation, the basic kind of laminar-like flame speed has to be adjusted to account for this additional wrinkling factor. So I think it would be nice to have validation of that argument experimentally. So so you can actually measure the wrinkling factor in a way, and then how that correlates with the overall burning enhancement. I think that would be very valuable.
That's what I discussed with someone yesterday to see to get ideas how to characterize these structures. Because you can imagine it's hard to get a reliable post-processing onto it, so you need to get measures for this. But I'm happy if you have some suggestions. Also, please let me know how to proceed with this kind of data. And I guess calibrating like the laminar flame speed is for many scenarios sufficient. I'm just wondering if you look at NOx or something, does this matter if you have different temperatures locally? How much does it matter? That's just things which we might need to consider. Thank you.
Any other questions? Maybe I have one. Do you also envisage to go into ammonia like combustion units?
If you give me the funding, I would do it. I characterized, we tested our engine for ammonia. It runs, not for these part loads. You really need to go to full load to have some combustion, but we added a little bit of hydrogen, and this is an option within this engine.
Then related to that, you said you wanted to measure NOx, or well.
Yeah. I have a colleague in Darmstadt, Stephen Wagner. He does laser absorption spectroscopy, and he's able to measure quantitatively, let's say in the exhaust port. That's what we have done already, presented a few years back, NO, N2O, NO2, ammonia, and so he can measure this in the exhaust port of the engine. So we could correlate it to different scenarios. That's something which I'm really interested in going for as soon as I have opportunity.
Anyone? If not, let me thank Benjamin for his work. And we have the next one. Ludovico, am I right?
Yes,
And Viglione?
yes.
Viglione. Indeed, two-stroke marine engines, ammonia, methanol, dual fuel combustion. So, ready? Which one is yours? So the floor is yours.
Okay. Thank you. Good afternoon, everybody. My name is Ludovico Viglione from Wärtsilä Two-Stroke Service, Switzerland. And I will present and introduce some work that we are doing in collaboration with Politecnico di Milano and the team of Professor Lucchini in the developing and work on numerical modeling on ammonia and methanol combustion system for large two-stroke marine engines. So in this presentation, I will go through some application of this model in order to develop a retrofit solution. Our company is basically working on the two-stroke slow marine engines in order to develop some retrofit solution for decarbonize the marine sector. Currently, we are working on both the fuel. This presentation will mainly focus on methanol solution because it's currently running on our test engine, and so it's something really concrete. In the presentation, I will focus more on the 3D and 3D CFD modeling with some remark on the methodology and correlation with the optical spray chamber analysis that we are also carried out in collaboration with CNR STEMS, formerly Steel Motor in Naples. And of course, this is part of a bigger work that is aimed to develop a solution ready for the market. Going into the some overview of the CFD application, as I said, we are working with the LIPICE package from Politecnico di Milano, and basically the framework is what we saw already in these days. So it's modeled in OpenFOAM version 8 with the device libraries. This is a standard RAND simulation with tabulated chemistry, and what is peculiar in our application is, of course, the dual fuel concept. So we are trying to simulate and model combustion for this new fuel, piloted with methanol injection. This is just the gas exchange phase that is managed with mesh mapping, as we saw also in the previous days. And of course, the combustion is also simulated and considered in these works. This is just a overview of one preliminary validation that we did on a classical engine case, so diesel, in which we, despite the significant dimension of the engine, we reached a good, let's say, agreement with the simulation experiment in a reasonable time. Now, going on some details of the procedure and how we proceed. Basically, as I mentioned, the first approach was to quantify and to characterize also these kind of new fuels, both methanol and ammonia. To do that and to decouple also a little bit the effect of the new fuel and the sensitivity of this thing, we worked with an optical accessible spray chamber that is co-designed between Wärtsilä, Switzerland, and STEMS. That is peculiar for the marine sector. So we feature two different positions for pilot and main injector. In this case, one particularity is that these injectors are typical of marine sector, that is not frequently found in the use. So we started from some simulation on this of this chamber, just to get some sensitivity on the model, on the performance, and to assess preliminarily how the model was responding to the reality. Of course, we went through the classical sensitivity, mesh sensitivity, and we will see later on chemistry sensitivity. As we may say, the model is, we reached a quite good independence on pressure, perfectly independence on between the medium and fine mesh. A little bit of difference can be seen in the spray evolution, but we may say that in any case, it's responding well with the experiment, and we will say later a direct correlation. Again, one of the main topics for methanol and even more for ammonia is on the chemistry part. On that, we also undergo some evaluation of chemical kinetics. We are using in this framework mainly the tabulated chemistry, but we also evaluated a direct chemistry resolution. Of course, to make it reasonable for industrial application, we made use of DLB foam and PI jack that has been developed by some colleagues now in Wärtsilä and formerly in the Aalto University. And what we can see here is that both the models are responding quite well in terms of pressure and ignition delays of this dual fuel concept, with I must say good timing, in sense that of course the direct kinetic is a little bit slower, but still reasonable. Some differences can be noticed on the flame development, but let's say that both the model for our approach are good. They can be maybe differentiated on other finer information like combustion and emission. As we said, all the sensitivity were responding in the same way, and luckily all of them are also responding quite well with the experimental data. This is an example of pressure trace taken from the optical spray chamber with an example of optical data and simulation, in which we can see the diesel injection, so the pilot, the methanol coming from the side, and isocontour on temperature that would resemble the same effect that we see on the in the optical chamber. So we may say that we can say that we are quite happy on the preliminary result. And so after this, we could have moved to the full-scale engine. This is an example of the application. So real engine geometry, the one that is currently, as we speak, running in our test facilities. And this is the application that we are targeting for. So dual fuel, pilot injection, and alternative fuel that can be methanol or ammonia. Now, how we used this model and what is the scope of this work? This has been used in a predictive way to assess a design of nozzle and some engine-related pre-calibration or parameters. And we can see here how this helped in the design of some nozzles in order to address for the new fuel. We can see here, for example, this is how it is important to design this new component in order to take account of the different lower heating value of the new fuel, and so the adjusted quantity like spray duration, injection duration, and nozzle dimension. In this case, a wrong targeting of the jet would reflect directly in a wall impingement and component stress. This is in fact one of the study, one example of application that I show here, in which we can see, for example, 3 cases of nozzle design and the process that has been done to optimize this selection. So basically, just moving from one selection to another, we will be able to reduce the heat transfer, heat rejection, and so stress on the component. In the picture, it's just a visualization of the stoichiometric fraction, and we can see that the 2 solution can also improve in case the IMAP and efficiency, and of course also the emission. This is still the same case, but evaluated on pressure trace and heat release. And we will see in the next phase that this is actually no more some speculation, but these are real, even if normalized, values of the engine that is currently running. And we can see that the model is responding quite well in terms of pressure matching and even more on heat release reaction. So this is basically our first step on development of this engine and preliminary validation. Now, of course, moving to the conclusion, we can say that the methanol diffusive concept have been correctly evaluated and validated in CFD experiments, both optical spray chamber, but also real engine. And the next step in this case are, of course, further development in the model, so that can be introduction, evaluation of different spray model, combustion models, and CHT consideration. And I did not mention in this presentation, but in the title, we are working also, of course, on ammonia, and so this methodology is going to be validated in this sense. This is from my side. Thank you.
Questions? Let me start. So you use tabulated kinetics. I was wondering how the 2 fuels interact on the table.
In this case, we used 2 different tables. So the tables are separated for the diesel and the second fuel, let's say. the assumption here is that actually the chemical interaction is not so strong. We are aiming for quite big fuel share on the second fuel, and the interaction is more on the thermodynamic part and not chemicals.
And your diesel injector is quite far away from.
Yes. Maybe for future application, we may also consider a table that includes both fuel, but right now
Most fractions probably. Any other questions? I have one.
I mean, well, from company's standpoint, they must have a lot of information about anything related to the marketability. What is the roadmap? There are multiple choices, as we know, for marine future, marine e-fuels. What is the current judgment right now? Can you say?
Okay, I'm not the person that can deserve a lot, but yes, in our as I said, our focus is to in our company we are trying to produce this retrofit solution for new fuel like methanol and ammonia. Of course, there is interest in this on the market on this solution. If you want to, if I answer to the question, the real roadmap is it's an unknown from everyone.
Is it pending the outcome of your research findings, basically?
Yes, but we can say that there are requests from the market already on this field.
This is strongly tied to the fuel cost eventually.
That's of course. We will be ready for the
availability, I guess. Anyone else? Maybe a small question on your heat loss simulations. You have to assume some temperatures, I guess.
Yes. Right now, it is a fixed temperature based on previous experimental value. Now, as I said, this is the first step. Now the engine is running. The hard work will start now in validation and refinement of the model. But still, we can say that first step is successful.
More questions? No, then thank you. Then our next speaker, Michele. It's a dual presentation.
Yeah, it's a dual presentation if it's not a problem. So I will start and then Masri will follow. Okay.
Very good. Very good.
Okay. Good afternoon, everyone. Our work today is about accelerating some slow simulations regarding fuel injections. The title is Accelerating Multi-Phase Flow Simulation with Neural Network Models in OpenFOAM, and focusing on transcritical flows. So this work is mainly has been done by Nasrin. She is a PhD student now finishing with my group. Previously, I want to thank Paniri who developed the base structure of this code. And I will present the first part today, starting from a quick background and motivation for, let me try, neural network to replace some heavy calculation inside the solver. I will show you quickly the governing equation and the thermophysical models that we are focusing on, and our CFD numerical framework works. And then we go into the data generation and model training for neural network model, how this has been coupled with OpenFOAM, and we show results on a test case, which is gaseous oxygen and liquid hydrogen test case. It's not exactly an engine, but it was, the work was conducted this way, and then summary and future work. So the context, maybe I can simply say that everybody here seems to be working on hydrogen or low carbon fuels, zero carbon fuel like ammonia, and I think our work fits into this context definitely. We are looking at hydrogen or other type of fuels. High volatility fuels like methanol or ammonia, where this type of numerical framework can be applied. And so some properties regarding the this two-phase flow. On the upper right, there's a chart which shows the compressibility effect on a single component, but also for mixture, it will be more elaborated. There are quite significant discrepancies compared to ideal gas, for example, on one side, and liquid on the other side, as an ideal incompressible, for example, fluid. So to take into account some physics more related to phase change or close to operating point near the critical point of the mixture, and or inside the dome, so in the two-phase region, we need to account for this aspect in a more accurate way. And so we developed, actually this was a project in collaboration with Professor Im at KAUST in the previous year, and we came up with a model which takes into account its effect for mixtures. And there are many parameters which can affect the injection, what happens from injection pressure to back pressure, temperature, nozzle geometry, and so on. Here you probably see, this is just over imposed. An isentropic expansion generally produces a, while the pressure goes down, the temperature drops a lot, so you can reach either two-phase or get close to the saturation line. Below is an example with ammonia. This is a two-phase flow where this area we experience flash boiling, so strong vaporization and jet behavior like a gas jet because of the expansion. And so these are examples where we are basically working on. In this presentation, we'll be focusing on this real fluid effects and how model works and how we try to simplify the calculations. Computational method. These are the canonical governing equations for a two-phase flow as a single fluid. Okay, so we have one velocity vector, but n species, and we do not track the interface. It's not like a VOF, it's a diffuse interface method. So the equations conserve mass, momentum, energy, and species for any number of species in general. We are limited today to 2 species. So for example, the fuel and nitrogen. And this can be coupled with turbulence model runs and LES. Our test case will be without any turbulence model, like a DNS, but also in a coarse situation, just to prove the concept of this neural network acceleration. A few words on the thermodynamics and the transport. So we have 2 ingredients in this type of work. So we try to consider an advanced equation of state for the mixture, which includes composition. X is the molar fraction of each species. And this is the typical, the simplest we can use among the cubic equation of state, Peng-Robinson. There are more complex, and with this we can capture much better the property near the critical two-phase flow region. And also we can correct the caloric property, let's say the enthalpy or specific heat and so on. The important thing is that what we have been doing here is basically introducing nonlinear mixing rules, so some combination to get the properties of a mixture with n species, not with just one. And there is a quite some complicated nonlinear solution required to get all the properties that you need for knowing locally density, enthalpy, CP, and also transport properties like viscosity and thermal conductivity. So we basically extended some of the this thermo package includes some modification to what generally is used in the context of reactive mixture. We have this chunk mix and also this mixture Penn-Robinson gas, which takes care of this nonlinear interaction between different species to end up providing the properties locally. This was the heavy part, because when we started from reacting foam, which is available in any open foam distribution, more or less, and put in this equation of state and the connected stuff, it ended up being 10, maybe 15 times lower than a perfect gas calculation. And we had developed different type of solver. The first one is the minimal modification with a change in the pressure equation and the frequency, including the update of properties like transport properties, like inside the inner loop for species and enthalpy. Then there is another branch of this solver which make use of the, I have to read here because that is a bit inconvenient, raw pimple central foam with the central scheme that today, this morning, Francesco Duroni presented, and which makes use of flat splitting and helps, accelerating the solution, but without taking care of the thermophysical aspects. So for the thermophysical aspect, I will be focusing on this upper one, which is the simple reacting foam with the modification regarding the real fluid properties I mentioned. And here, maybe my last slide before I pass the ball to Nasrin. Previous validations. So we have applied this to spray A on the left-hand side. Other cases with hydrogen and oxygen, the same test case that we'll be using today in the middle, and on the right to hydrogen jets, trying to validate the results obtained by this model. Here, for example, I'm showing below an image that shows what we are talking about, a jet, a mixing layer, and a gas jet at high pressure. And here we were happy with the predictions, which are in agreement with the literature published already on this type of problem. And we have pure gas on one side, pure liquid on the other, two phase in this region, and the behavior of the temperature depending on the mass or molar fraction. Here we have a validation regarding the liquid oxygen hydrogen mixing layer in terms of thickness as we move away from the lip. And here a validation of the of an hydrogen jet. Here a couple of time instances, and here a axial velocity with a high speed and the shock and the structures following the jet. So we can consider this solver as quite good for running this type of simulation. The only point is that it takes some time. So we have investigated how to replace in this real fluid reacting foam the thermophysical package with a neural network algorithm trained on data set generated in different manner, because this opens for different possibility. At the moment, we just use our own library to generate the data, and but it can also be trained against more accurate data set calculated with even more complicated thermophysical models for more species. And then we need basically to couple this NN model with the OpenFOAM. And we have explored two ways. We'll be talking mainly about this NICE, which is a direct C++ inference, while there's also another possibility of doing it with Python and APIs. And okay, this is long. So what we are, sorry, can I go back? Okay. What we'll be showing is basically that on this test case, the liquid oxygen, gaseous hydrogen, the middle one of my previous slide, we'll be getting the same accuracy with almost 10 times a reduction of factor almost 10 on the clock time. So with this, I'll pass the ball to Nasrin. She can continue and explain her work. Thank you.
Good afternoon, everyone. My name is Nasrin. I'm so happy today to share the results of this project with you. As Michele mentioned, the purpose of this work is to facilitate the calculation of the thermophysical properties using the neural network algorithm instead of the thermophysical library of OpenFOAM. First, we need to generate the data. There are two ways to generate the data. The first way is using the real fluid solver of OpenFOAM, and the second one is using the Karnos library, which comes from the IFP Energy novels actually developed there. So the Karnos library provides us a toolbox to initialize the data and also create the equations ourselves, and also get the thermophysical properties as the output from valid numerical and simulation data of the Karnos library. So we use the first method, which is OpenFOAM. We initialize the temperature as the inputs. We consider temperature, pressure, and composition, and as the output, we will have the density. X TT for the temperature is considered composition, enthalpy, and also pressure. So you see all of the outputs here. These outputs are trained separately, each of them. So in this slide, you can see there are some distributions which are non-linearly for almost all of the outputs except enthalpy and temperature. Just keep it in your mind that I will explain it more in the following slides. Okay, for the ML, for the machine learning method, we use the neural network method in which each output is constituted from the weights and a bias from the previous hidden layer. So in this case, we consider two hidden layers, including 100 number of neurons for each hidden layer. And as the activation function, we consider the ReLU activation function. So from the Python side, for the computations, we use Pandas and NumPy libraries. And for fitting the model, we use Keras and TensorFlow with making use of the hyperparameters. So the important part here is to scale the data between a specified range. For example, between 0 and 1, we did it because all of the inputs and the outputs should be in a specific range that neural network can find a good relative between the data inputs and outputs. So this is important in this case. And also another important factor that we should take into account is choosing the hyperparameters. So the hyperparameters is by experience in our case, because in all of the cases, we should do some experiences to find the best hyperparameters. One of the most important hyperparameters is learning rate. You can see the effects of learning rate with making different learning rates. The actual, for example, density versus the predicted density will be so different in a different manner. Another important hyperparameter is the number of epochs. You can see the effects of the number of epochs for example, so our study is about the relative errors, okay? So from 100 number of epochs, you can see that the relative error in some points goes, for example, to 200%, and here for 1,000, for 10,000 number of epochs, it is near to 100%. Okay, maybe you ask that, okay, 100% of relative error is too high, so it doesn't matter. It is not acceptable in our case. So we need to reduce the relative error to less than 1%, maybe, for example, 0.1%. So when we have a best relative error, we have the better in performance of the neural network from the OpenFOAM side, because OpenFOAM side is very sensitive of the network, so we should take care of this relative error in that case. As you can see, in this case, for example, for the compressibility, we consider the relative error goes to more than 50%. Okay, one approach in our case is to split the data set into different ranges. So we did split the data into different ranges. You can see that the relative error becomes less than 1% in each case. And but this method in OpenFOAM and in our case, it is not applicable because we need a criteria to initialize the data, and maybe we need a lot of rain, so it's a bit complicated. So we try to train this network just for each output, once for each output. So what did we do? For example, for the compressibility, we did the logarithm transformation, and for other nonlinear distributed outputs, logarithm transportation, and also for choosing the data to train, which is very important, we choose an adapted data range. So the adapted data range means that we choose the data input and output data close to our test case. So it helps us to have the best results from the neural network point of view. So I mentioned that the choose of the hyperparameters depends to each case and each test case separately. So we choose these hyperparameters that you see instead of, for example, the learning rate and the number of neurons and also the number of hidden layers. All of these, they are the hyperparameters. Okay, for the implementation of NN inside OpenFOAM, we have two approaches, as Michele mentioned. One approach is a nice approach, and another one is PythonFOAM approach. The nice approach needs Eigen, HDF5, and Rapid JSON libraries to compile inside the OpenFOAM, inside the C++ parts of OpenFOAM, and also for the compilation. From the previous level, we have all of the weights and the intercepts from the Python model, from the training Python model, and we put all of them here in a nomenclature, and it will be translated to HDF5 and JSON files. And then from the main body of the OpenFOAM, it reads all of the JSON and HDF5 passes, and using a single inference approach. So in this way, the nice code is implemented inside OpenFOAM. About the PythonFOAM approach, it is another approach. We use the Python models in the test directory. So all of the inputs, first we need to initialize NumPy and Python, and then all of the inputs from the Python side goes to NumPy, goes to the Python modules, and the calculations are done there. And then the output from the Python modules comes back to the OpenFOAM and will be replaced, for example, with our desired property. Okay, you see the Pimple loop. Inside the Pimple loop, will be, all of the thermocalls will be removed, and the Python modules and Python models will be replaced. And then specifically in pressure equation, the density will be replaced instead of the thermocall, and the Python models will be replaced. So the model that we consider is it is a mixing layer of liquid oxygen and gaseous hydrogen. You see also the boundary conditions. Michele explained about the test case before. So we will consider four different, in this slide, I want to show you the effects of the relative error in OpenFOAM side. Okay, how this relative error affects the results. The first, you see that in the first column, the relative error goes, for example, more or less 50%, okay? And without any transformation of data and adapted data range, you see some noisy fields and also some disturbances in temperature, density, and hydrogen fields. In this case, in the second column, the relative error comes more or less 30%, so better performance of NN, better accuracy of NN. We can also see some noises and some disturbances, but the velocity field is developed. And in the third case, which is the best case that we reach to it, it is the relative error less than 1%, and you can also it is a clear field, and you don't see some noises and disturbances, and it is the similarity to the direct real fluid model. This is the direct real fluid model is very high. So this is the closest case to the real fluid model that you see here. So we will continue with the last case, which is the best case from the relative error point of view. So we consider this case. And then in following times, in 1 millisecond, you see the good agreement of the NN model with real fluid model in considering the mixture model involving the transport properties and also real fluid model. The quantitative, you see also the quantitative results in which the mean and mean square error is compared, obtained from the some time averages from 1 to 4 flow-through times from 1 millisecond to 1.2 milliseconds. And you see that it has a very good agreement with the direct real fluid model. Also, this is the scatter plot of thermodynamic states of the mixture temperature and also the hydrogen mass fraction. We reach to the interesting part of the work, which shows that the total execution time of NN model is more or less 3 times faster than the real fluid model. But for each iteration, it is close to 7.5 times faster. It's because the real fluid model accuracy is more than the NN model. So the number of iterations of the real fluid model is less. I mean, the direct real fluid model is less than the NN model. But if we can reach with in decreasing the relative error, if we can reach to the number of iterations of the real fluid model in NN, we can reach to 7 times faster calculations than the real fluid. So I finish here, and Michele concludes the work.
So we can just conclude and just summarize, our work. As you saw, basically we have presented a way of coupling neural network directly into OpenFOAM to replace physical properties. We call this solver NN reactive foam, basically. And there is some plan of applying this to, as I mentioned, hydrogen, when we consider relevant high pressure and the effect of the high pressure in the injection. And other, like ammonia or methanol, fuel, low volatile fuels, which will exhibit some expansion, sorry, I'm pointing the right expansion like this, and the two-phase region can be treated with this real fluid approach. I think that's all on our side. I just want to thank all the group and Faniri, who is not here. So thank you very much.
Thank you, Michele and Nazarene. Questions for both? You can address them separately if you want, or together.
Just one question about number of iteration. Do you mean that you need to deploy a smaller time delta T? Yeah, the number of iteration is different. So it means that you have to employ a smaller delta T for the and then.
It means that the number of iterations means that, for example, for the real fluid model, in each time, for each calculation, it takes less number of iterations to converge. So it means that the accuracy of the
Piso loop.
Yes.
Okay.
Yes, in the Piso.
So the under relaxation in the Piso loop, you have to increase the number of.
Yeah, the other approach reaches tolerance that you said earlier, and then NN at the moment takes some more iterations.
So that is not a physical number of iteration.
No. It's the internal, the overall. Yeah.
Yes. Okay.
Anyone else?
Thank you for the presentation. So my question is about the adoption of neural networks. So I was wondering, what's the real advantage of using a neural network over other simpler regression approaches? I mean, it seems that the function you are trying to approximate using a neural network is quite regular, just a function of the input variables, if I'm not wrong. So My feeling is that maybe you can reach the same result using simpler methods. Just my feeling.
Which method, for example, just name a method.
Polynomial regression or radial basis function.
It is impossible for the polynomial regression because the neural network, because we need to use a deep learning method rather than the machine learning method. So neural network basically works with the deep calculations of the relation between the inputs and the outputs. And as I showed you in one slide, the distributions are nonlinear. I mean, we encounter with some nonlinear properties, which are thermophysical properties. So we tried all of the methods, simpler method before, and we could reach that the neural network acts better, can have the best prediction of this relation between the inputs and outputs. So, for example, if you use polynomial regression rather than the neural network, it is something like the relative error goes, we can't reach less than 20%, 10%, which is not acceptable in the case. Because OpenFOAM immediately diverse if you can reach to a good number, a good relative error for the case. A neural network can predict these waves and intercepts in a very good way because it's in the backend, it is designed for this kind of calculation, for nonlinear properties and something like this. So the neural network is basically the best method here. So our case is just 2 hidden layers. We can use more, we can test more complex hyperparameters and characteristics of neural network to make the better. So we are working on this race. But there is no simpler method to do this, to do the machine learning method inside OpenFOAM. So this is a simpler and also the best method that we can use for as experience, and as the other groups also worked on it.
Yeah, it seems like other groups are also doing similar thing. For example, she spent 3 months in IFP, Paris,
Yes.
working on this, and they were also doing similar approaches
Yes.
for the same type of problem. Yeah, probably there is room for doing it better or in an alternative way, but
It's like, for example, for the chemistry part, if you want to take into account the chemistry parts, it will be more complicated. So it needs to be a neural network. Without the neural network, machine learning is not a powerful tool to can predict these kinds of complex relations between the data. So from the experience, as I said, we should choose these kinds of relations and all of the parameters from experience, and it's very time consuming. Unless we can reach to a unique, and I mean more or less a good method and good model can be used just for the thermophysical part. And it would be nice because it is super fast and we can extend it to another model.
Thank you for this elaborate answer. There was maybe a question.
It's a follow-up on this one. How do you decide where the complexity of the physics comes from and how it's treated by your neural network in this case? It could be maybe also just a more advanced feature extraction that would enable a simpler algorithm.
The advanced features, what do you mean? You mean the advanced hyperparameters?
No, advanced feature extraction. So how do you define your input variables? You can just take them, or you can combine them, or you can do exponential of them, or logarithm of them.
Okay. It is my experience.
These are new features that could be used.
Okay,
and
that's
then maybe enable a simpler algorithm.
Yes, that's right. For example, we use for the transformation of the data, we use logarithm transformation, which I use also another kind of transformation of the data. But the logarithm for this kind of data works. So we can try also another kinds of mixture of the inputs and also transformation of the output, how we can scale the inputs and also the output, just input or just output, the transportation of just inputs and not the output and vice versa. So it is such like an experience that we can get it. Until the time that we have some other works related to it that we can reference to the other works, to reduce the time of this kind of things. So we spent a lot of time in order to understand how can we do it in the best. So yes, there is no specific route in our book.
Quick,
Very short one.
yeah, sure. Yeah, quick. Just do you have some good sense of the optimal number of hidden layers and neurons?
Yes.
And also, how do you ensure that these results kind of complies with some certain physical conservation principles? Whatever that means. This is related to like a physics informed neural network. So in the loss function, do you enforce some of those physical constraints to make sure they are not violating?
Well, the conservation of mass, momentum, those things are on the transport equations, as long as we provide the right density and the other properties. But yeah, on the training side, we didn't do any check on these aspects.
You didn't find any problem with that?
Well, I mean, the problems were, I think, related mainly to have a very good accuracy, or not noisy, not even one outlier on the density or compressibility. Those two things are the code is very sensitive and blows up immediately. So on other variables, there's no problem if you have sometimes a spike on an error, but it doesn't create any problem. On those two, it's very important to be more precise as possible.
The number of neurons and the
how many
layers?
We used 2 hidden layers, each 100 number.
How did you come up with that number?
The first I used is an optimization tool named Optima. So regarding to the outputs and inputs, it gives you something around that would be good for your case. So at first I use Optima to predict, to see and just watch the outputs regarding the experiments that the other groups did. And then I make use of the data from the Optima, and then by experience, I check it.
Thanks for your answer. I mean, we have to move on.
Thank you.
Thanks. And that's the last one of this session. It's Vincent's Q.
Yes, exactly.
Modeling of turbulent hydrogen combustion. That's a broad topic.
All right. Hello, everyone. For bearing with me the last 15 minutes before the coffee break. I want to talk about some projects and some stuff we've been working on in our institute regarding modeling hydrogen combustion. And this is not only my work, but this is also mainly the work of 2 colleagues of mine. Yes, so the work in general will be split in 2 parts, sort of. First, I will go a little bit, like a very short introduction into the challenges of modeling hydrogen combustion and also sort of the characteristics of hydrogen combustion. This will just be 1 slide, so then afterwards we will straight go into our modeling approaches. And first we will look into chemistry modeling, and then specifically into flamelet modeling, and then secondly we will go into the turbulence chemistry interaction and our recent work there. So I guess most of you are quite familiar with characteristic of hydrogen, and when it comes to modeling, besides the reactivity of hydrogen, also the high diffusivity of hydrogen is quite crucial. And you see here some nice experiments from Aachen, and then next to it you also see fully resolved simulations of us. We performed it in OpenFOAM. By the way, every time you see this small logo at the top, you see an OpenFOAM simulation. And you see you have these small corrugated structures inside the flame front, and these structures need to be accounted for and also need to be modeled. You saw also the relevance of the work in the presentation of Benjamin Böhm a few hours ago, maybe an hour ago. Where does these these structures come from? These are called thermodiffusive instabilities, and this is just an instability where you see a demixing and a stratification between the in the premixed hydrogen, which lead to that positively curved flame regions are further enhanced in the flame speed, and negatively curved flame regions are have a lower reactivity. So as I mentioned, this part will be sort of split in two parts. First, we will look into chemistry modeling, and here in particularly flamelet modeling. Flamelet modeling is, so you have some sort of flame sheet, and then you have the flamelet perpendicular through the flame sheet. This is quite a commonly used approach, as you might all know. And the question for us is, when we started this, is does it actually work? And if not, what do we need to include and what do we need to do in order to make it work? So that's the first question. And then the second question is regarding turbulent flame or turbulent chemistry interaction. This is just a very short schematic. You see a flame here, and then some inflow from the bottom. We have here one flame with hydrogen and one with methane. Both have the same laminar burning velocity, and what we did in the bottom, we applied the same perturbations in the flow field, and then saw how the flames react to it. And what you can see, just from a very basic visualization, that the flames behave quite differently, and that's the thing we need to ensure that the model actually can do this thing. What we see. These flames have the same laminar burning velocity. However, in turbulence or whatever fluctuations, you see a very different flame speed. And so far, none of the TCI models, turbulence chemistry interaction models, really able to capture it, and that's what we tackled. First, let's talk about flamelet modeling in terms of hydrogen combustion. Therefore, we concluded fully resolved simulation open form of a spherical flame. This is 2D. We applied a mixture average diffusion with a direct chemistry approach, lean hydrogen at ambient conditions. And what we can see, that you have regions where you have positively curved flame and negatively curved flame. This is all as expected. However, we are interested how the flamelet models actually perform on this flame. So therefore, we took out a portion of this fully resolved simulation and did an a priori analysis, also an a posteriori analysis, but I will just focus on the a priori results here. So we have here our reference data. Here you have the temperature, and here the OH mass fraction. And when we see, okay, we apply just the standard flamelet, also including already enthalpy, which is sort of more advanced already, we see still that there's a large discrepancy between, especially in the OH radical, between the flamelet model and the reference data. Moving further, so there basically was a need to do something about it. And what we did is we, instead of using standard flamelets for our flamelet approach, we used curved flamelets. So basically you have like sort of, you can see this as a curved flame. So, and the curvature here is parameterized using the H radical. And what we could see is that actually if we include curvature into our base model, into the flamelets, which is then represented in the flamelet table, we can drastically improve our model and actually predict also these instabilities. Moving further, this one is now the turbulent full resolved simulations. This is premixed hydrogen air in the so-called slot flame. This is also a lean mixture at ambient conditions, roughly 350 million cells on 20,000 cores. So that's also what's capable of doing an OpenFOAM. This is what an instantaneous snapshot of the flame looks like. And you already can see here that this is a color bar of the H radical, that we see very strong regions where you have a high H or high, where we have a lot of H radical and where we have little H radical. And now the question was, okay, we have our improved flamelet model. How does this perform in the turbulent case? And actually, what else? What other phenomena do we need to include in our model? So here I brought the composition space of this particular flame. So we have here the progress variable and then the enthalpy in colored. It's coloring by the equivalence ratio or Bilge mixture fraction. So now, first I want to show you the results of what's actually the effect of our curved flamelets. And you can see here when we increase the curvature in our flamelet approach, then you can see that we have that we cover like this large region of the composition space. However, you can see also on the top here, there's still like a large part missing. And what this actually means, okay, when we want to model this and represent the actual composition space, we need to capture the whole composition space with our original flamelet data, with our flamelets. Therefore, also, besides curvature, we need to account for strain. So when we included also strained flamelets. And what we now can see is that the strained flamelets actually do recover this region. So our conclusion from this was that, or in a turbulent case, in these conditions, you both need curvature and strain to correctly predict the flame, or to have the correct composition space. Sort of summary. So let's hop right into the turbulence-flame interaction. And here in particular, we are looking at the ATF model, the artificial thickened flame model. This is particularly interesting because it works also with direct chemistry. So when you want to perform when you want to use direct chemistry, for example, in the engine or in some other configuration, the turbulence chemistry interaction, is then the ATF model is the way to go there. What it does actually, this is schematic, obviously, you have some computational grid and then the actual flame lying inside, which is not captured here. So what you do a coordinate transformation and you thicken the flame artificially, what the name also stands for. However, yes, you can also see this flame is way less wrinkled compared to the actual flame. And from this, when you don't do anything, the fuel consumption would not be equal. However, this one is already a known problem. This one's also a problem for all fuels. And there has been there's been several approaches for an efficiency function, for a so-called efficiency function. Also, major work has been done there from the France community, from the French community. And what this efficiency function does, it just basically ensures that the consumption speed of the ATF model of the flame, which is thickened, is equal to the consumption speed of the laminar. The laminar. No, not the laminar, but the actual flame. So it predicts the wrinkling by a wrinkling factor and then applies it to the transport equations. However, this efficiency function is not yet, there's no efficiency function for hydrogen. And this is exactly what I'm going to show you in the next couple of slides. Why is this necessary? This one is also just an example. Here on the left-hand side, you see again our fully resolved simulation of the slot flame, which I've showed you before. And then you see, okay, we just coarsened the grid. Instead of the full resolve, we also implemented an LES model. And then we had a thickening factor of 4 and a thickening factor of 8. And what you can see is that you have way less corrugation on the flame front, which is per se not the problem. But what's really the problem is that the flame elongates. So that means that the turbulent flame speed is not properly captured by the ATF model so far. Exactly. So there's the need. The current TCI model cannot predict the correct consumption speed for hydrogen combustion. Now, what we did there is also, I think, in the hydrogen community quite well known. We had a full resolved simulation of a 2D planar flame, being hydrogen conditions, and we let this just run over time for a long period of time. And what you can see is you have these instabilities forming. This we saw already before. And you can also see, even in this laminar case, you have a huge increase in the consumption speed compared to the just planar flame, which is the initialization for this one. Then this will become important later. Yeah, you can see the average increase also in the consumption speed is way higher than the original planar flame. So you can see these thermodiffusive instabilities lead to a significant increase of the average fuel consumption. And there's also been work done by the people of Aachen tabulating this. However, now what do we do with the information? We transferred this to the ATF approach. And what we did there is we basically have this is the same domain. And now we have like a thickening factor of 1, which is no thickening factor of 2, which is twice the flame thickness, and 4. And what you can see is, in general, the ATF model does not dampen out like all the instabilities, but instead only the scales, so especially the length scales, are altered by the thickening approach. So what you can see, you have like these small flame fingers here, and these become twice as large and 4 times as large, so they scale with the thickening factor. All right, what does this then now apply to the consumption speed, which we're eventually after? Well, for this one, we did the same simulations as I showed before, but now we've varied the domain height in order to trigger different length scales inside the flame front. So when you have like a very small domain, you only have like, for example, 1 cell inside, but when you have a very large domain, you have like the flame fingers and all sorts of length scales inside the flame front, like instability length scales inside the flame front. So we did that, and this one is, the blue one is the one with thickening factor of 1. And now you also can see F2 and F4, and these look quite similar, but actually like they look similar but not the same. So what we can see, so we have when we have very small domains, the thickening actually dampens out all the instabilities and the flame remains stable, and therefore we don't have any increase in the consumption speed. However, when we look at, for example, a specific domain and we want to predict the flame speed, we need to change, or we need to have an efficiency function which takes into account the constraining length scale of the flame. This could also be in turbulence, maybe like an integral length scale, for example, and obviously the thickening factor. So we constructed an efficiency function which takes into account like the global length scale. For example, here it was the constraining domain size, then the thickening factor, and then some flame intrinsic parameters. So for example, you see this for example is scaled by the critical or by the smallest instability size, which is inherent to the mixture, for example. And now when we apply this to our model, so these points are all a posteriori. So actually we applied the model into the simulation and then let it run. We can see that for all thickening factors, so F2 improved, F4 improved, we see that we can predict the exact same consumption speed in this laminar case. So our conclusion from this is that we have actually shown that we can extend the artificial thickened flame model in order to accurately predict the flame speed enhancement due to the thermodiffusive instabilities. All right. There was probably quite a lot. Just a short summary. I've talked about the chemistry modeling and specifically about the flamelet approach, which included curvature and also stretched flames. I talked about the turbulence chemistry interaction, specifically the artificially thickened flame model, and how that we have extended the ATF model in order to accurately predict the consumption. Now comes the best part. Actually, we have the models developed in very easier configurations, so to say, which was necessary because in the engine you can't. There's so many effects which interact with each other. But now we're quite confident when we have the chemistry modeling and the turbulence chemistry interaction modeling that we now want to apply these models into the internal combustion engine, in the Darmstadt engine, the engine Benjamin showed, and hopefully we see an improvement there, and we can accurately predict, all sorts of stuff. Well, now this is the end. I want to specifically thank all these people down here. As I said, this is not only my work, but also the work of my colleagues. And I'm open to your question. Thank you.
Thank you, Vincent. Questions? Well, first, you look very serious.
No. I can do the same. Can I ask you? Yes, thank you very much. Very interesting activity. Really, I'm curious about the tabulation. How do you tabulate the carved flamelets?
This is a good question, and it's called the composition space model, where you, instead of solving for the physical coordinates, you solve for the progress variable, for example. So you have like a coordinate transformation, and as far as I understand, so this is just it's not as easy as straightforward mathematically. You do have some parameters and some additional terms which do include, for example, the curvature or the strain, and then you can vary the curvature and the strain. And
I can maybe
explain it better.
You know that if you have a non-premixed flamelet, you could do this either in physical space or in composition space, mixed refraction space. So what we developed over the last couple of years is basically a consistent formulation in progress variable space. And so you can solve now composition in, premixed flames in composition space. Now, why is that important? Because you can now formulate this with both strain and curvature separated. You're not bound to any combination of strain and curvature, and you can basically vary them as you like. And what you can especially do is also go to negative curvatures, which you cannot do in a real counterflow flame. You would not be able, because that is an unstable physical flame. So, and then you can tabulate this. And I think also nicely connecting to the previous talk, if you really tabulate all of that, positive curvature, negative curvature, positive strain, all of these, it gets a 5-dimensional table, which is extremely difficult to tabulate, and that's where we use neural networks.
Follow-up question, jump in.
Yeah.
So for the model, the curvature or the strain is given as a parameter, if I understand. And if you see the trajectory along the progress variable space in the turbulent plane, the curvature might be changing from the upper side to the burn side. You also consider this one, or you just set them constant for one plane?
You can do either one. It really is a question of how you do the flamelet. So in the flamelet tabulation, you would do this. You take one value for the curvature. You still have a curvature distribution over progress variable space. Yes, you could do this. But as always in flamelet models, if you use a tabulated version, while you go from a lower to a larger progress variable, you can trigger, or you can actually ask a different part of the flamelet table. But you could do this also in the generation part. But I think this is too much of an effort unless we need, if it's necessary, we can do it. So far, it's not necessary. But overall, the physics are included. Sorry to take
it's quite complex. It's true.
One PhD student's lifetime, yeah.
Yeah, one PhD.
I have another question. First of all, thank you very much for the very interesting talk. I have another question about this artificial thickened flame model. And you show you can reproduce the curve. It's like somehow a scaling law there. And I'm wondering if you change the phi, could you also reproduce it, or is just for the given phi?
So until now, we have only worked on one equivalence ratio, but in the model does not make any assumptions there, or the extension also. So it's basically just a matter of having extra simulations and then running those also with the scaling law should be similar. So it's matter of fact just a matter of running simulations and then extending the efficiency functions also to the other mixtures.
If you need a change, you can easily give that along with the model. In fact, if you do ATF for strained flames, then basically the entire ATF transformation breaks down because it's only for unstrained flames. So what you need to do is a strain correction. If you have higher F values, higher thickening factors, something beyond 3, then you actually would have to correct for this. And what we do is we just include that as part of the flamelet table, that you locally look up another parameter. Like you would look up diffusivity, you also look up one model parameter more to make it consistent. So it's not a showstopper.
No.
How many additional equation you need to solve?
For the ATF model?
Yeah. No,
for the flamelet model. Yeah. So how we do it, we transport the major species and then reconstruct the mixture fraction, and this is then the lookup, or one of the lookup variables for the table. So I mean, depending on which table you're using, but you also use the curvature and the flamelet.
So you solve for each mixture fraction species.
Yes.
Yes.
Okay.
And that's not a lot of computational overhead because the reaction rates come from the table. And in fact, especially when you think about LES, in the end, there's a lot about differential diffusion, partially resolved. Now we start to partially resolve the differential diffusion part in the LES. So that allows you to actually construct a consistent mixture fraction, not just transporting one mixture fraction with one assumed Lewis number. You don't have to do that anymore. You just construct from the major species, construct the one mixture fraction that you also use for table access. And then you still don't have to resolve the fine structure. That's still the benefit. Otherwise,
And then we should conclude the session. It's time for a break, right?
Yes. Yes.
People might argue that you could use the detailed chemistry in hydrogen combustion, but you cannot because you would have to resolve the reaction. There's no way that you can resolve the thin age use anyway. You transport the H2O by you. More, but again, the trick really is the old narrative of so that narrative has changed. So really is we don't have reactions on our structure anymore. This was always the case. The reactions on structure. And it's